his discussion, his presentation, well, how it is will be helpful to the research community, especially. Several are waiting for the Google in the Google Meet. And there are other scholars and students, participants are waiting outside in the streamline of the YouTube. And shall I invite Professor Kusubowiski to the today's workshop? Shall I start the presentation, Professor? Or you have to say something and then start? What
okay,
about, Professor? Is it?
Are you talking to me now? I'm sorry.
Yeah, I'm talking to all, Professor. Yeah. Now just I have to asking you, Professor.
Well, I'm very happy to participate in this proceeding. Do you hear me? Okay, yeah, just wanted to make sure. So I'd like to thank you very much for your kind invitation to this workshop. I'm very happy to be able to present some of my work here. And hopefully we can put my presentation on the screen. So I don't know how I can follow it otherwise. I mean, you have my presentation there, right? How do I see it on the screen? Or should I just look at my screen and tell you to move the page, or what? I mean, is everyone there able to see the presentation or not? I emailed this presentation. Okay, so I see it on the screen. It's kind of a small screen, so can everybody see the screen now? Okay, so shall I just talk about all of this and then somebody else will control the screen, right? Somebody else will control the screen, is that right? Okay, so let us get started then.
Yeah, Professor.
We have a little bit of issues, so we lost a few minutes, but I think we can still proceed and go through the presentation. So can we have on the screen, please, the presentation? I don't see it now. Okay, very good. Is it possible to increase the screen a little bit? It's kind of small. If not, it's okay.
How is now? It is okay.
Okay, all right, very good. So, all right, so shall I get started then?
Yeah, Professor. Yeah, please.
Okay. Well, thank you again for your kind invitation. I will be presenting this work with my co-author, Professor Chris Podgórski, with whom we work on this research. So the title of the presentation is about the Shibuya distribution. So we will talk about one particular probability distribution and some extensions. And we will go through some fundamental properties of this model. And in particular, we'll be looking at some relations and applications to extremes. All right, so this is what this is about. It's mainly connects with distribution theory, and there will be many different distributions mentioned in this presentation. So can we please move to the next screen? Okay. All right, so let's begin the presentation. We are actually looking at the formula right there on top of the screen. It's our formula for the random variable n. And this is what is known as Shibuya random variable. So the probability of n is equal to this product there. This distribution has quite a bit of history. It's been introduced in 1979. It was mentioned in the paper of Professor Shibuya. And then it's been studied over the years. It appeared in a few papers in the 90s, and then in 2000, people studied this distribution. So can we please move on to the next screen? Thank you. So the best way perhaps to understand this particular probability distribution is through the waiting time representation, right? So the best known waiting time distribution is perhaps geometric random variable, where when we have a sequence of trials, Bernoulli independent trials, and each one with equal probability, then we can study the waiting time to observe the first success in a sequence of Bernoulli trials. Then you get a geometric random variable. But different probability distribution can also be understood in terms of the waiting time distribution. So in this case, if you look at formula number 5, we're basically looking at probability of success is equal to alpha divided by j, where alpha is a fraction less than 1. All right, so this is the probability of success on trial number j. And as you can see, that probability becomes smaller and smaller as the trial number is increasing. So in this scheme with the Bernoulli trials with this particular probability, if we define a waiting time distribution n, then that distribution will follow the equation on top of the screen presented in formula number 4. So first we have n minus 1 failures, so we multiply the probability of failures, and then the very last one is the success, and that's precisely the probability that n is equal to n. And, you know, basically, if we don't get a success quickly, then we're going to wait a very long time to obtain the first success because of the decreasing probabilities. So we will generalize this distribution a little bit and study what's called the generalized Shibuya distribution later in this presentation. Can we please move to the next screen? All right, so our generalization is now presented in formula number 6. So it looks very similar, except we have additional parameter v that is in the denominator. So now we're looking at Bernoulli trials with slightly modified probability of success. And then again, we're looking at the probability distribution of n. We call it generalized Shibuya distribution. And the basic representation of the probability now is provided by formula number 7. All right, there's some particular special cases of this distribution, includes the Shibuya distribution itself. This is when v is equal to 0, and then alpha between 0 and 1. Then another special case is when alpha is 1 and v is positive. This is a special case of discrete Pareto distribution. We also have another prominent discrete distribution called Yule distribution. That one arises when both alpha and v are equal. And if alpha and v are equal and they're both 1, there is also a relation to a random records process. I think that would be described on the next slide. Can we please move on to the next one? All right, so let us quickly go through some of the special cases. So can we, I don't see the top of the screen. Can you scroll down a little bit, just a little bit? Oh, maybe it is the top. Okay, so here is a special case of discrete Pareto distribution when the parameter alpha is 1. That distribution in formula number 9 is another interesting probability distribution called discrete Pareto. Basically, it comes by discretization of continuous Pareto distribution, or I should say Pareto type 2 or Lomax distribution, with the formula on the bottom of the screen. So if we discretize that one, we get the discrete Pareto distribution with formula 9. And that one can also be obtained in the scheme of waiting for a first success in the series of Bernoulli trials, where the success probability is now given by formula number 10. All right, so let's move on to the next screen. Yule distribution is another special case. So here the independent Bernoulli trials have probability given by formula 12. So it's alpha over alpha plus j. And again, n is the waiting time for the first success to occur. So it should be noted that many of these distributions that I've mentioned, discrete Pareto, Yule distribution, as well as Shibuya distribution, along with the zip distribution given by formula 15, all of these distributions are what we call heavy-tailed random variables, where the probability of n actually decreases like a power law when n goes to infinity. So it's, they provide a very important empirical tools to study data where the probability of large events is not negligible. Can we move to the next screen? Okay, and then with the theory of records, one can also connect with these kinds of distributions. So if we have a sequence xi of independent and identically distributed variables, and then we fix the first of this variable x0, and then we're looking at the very first one in the sequence that exceeds all the previous values, then it's called a record. We say the record has occurred. And then subsequent records are defined in exact same way. So if we have a sequence of Bernoulli variables associated with this case, then basically these Bernoullis indicate whether or not a particular xj in the sequence is a record or not. If it's a record, then the value is 1. If it's not a record, then the value is 0. And in fact, the probability distribution of those Bernoullis are given by formula 16. It's studied in the classical random record theory back in the 60s. So if n is the waiting time for the first record to occur, then the probability distribution of this n is then given by formula number 17. So this particular distribution is actually both a Yule distribution when alpha is 1, and it's also a discrete Pareto distribution with alpha and v both equal to 1. So there are many connections here with other prominent distributions, in particular these heavy-tailed distributions such as Yule, discrete Pareto, and so forth. All right, can we please move to the next screen? All right, very good. So, so let's study this generalized Shibuya distribution. We again are looking at formula number 18. So we're given the probability that the jth Bernoulli variable is 1. As you can see, these probabilities are decreasing with j, so it's becoming harder and harder to obtain that success as when you are far away into the sequence, and when you define n to be the waiting time for the first success to occur in such a sequence, then the probability distribution of this n then becomes, formula number 19. All right, so that's what we call generalized Shibuya distribution. If the parameter V that needs to be greater than alpha minus 1 in order for this to work, if you notice in Formula 19, we must require some connection between the two parameters, alpha and V. So if V is equal to 0, then alpha must be less than 1. And in this case, we get the classical Shibuya distribution given by formula number 20. So Shibuya is the special case that arises when V is equal to 0. So actually, later in this talk, there will be a lot of information about Shibuya distribution, the classical one that really has many fascinating properties that, some of these properties we're going to go over in this presentation. So when we use the notation GS in this talk, that stands for generalized Shibuya. And there are actually two cases of the distributions, very similar to the two cases of geometric distribution. We can actually count the number of failures or the number of successes when we use the waiting time, and the values basically differ by 1. So when it says GS1, it means the distribution that starts with 1. It's the number of trials that are counted. Or GS0 means we're counting the failures. And that these two random variables simply differ by 1. All right, so does anyone have any questions before we go on with this? Is this all clear? Let me pause for a second, and then, so let's continue on to the next page.
Yeah.
Okay, so so here are there's some information about the generalized Shibuya distribution with alpha equals V, which is actually what we call Yule distribution. It's a special case. There is some connection here. I think we can skip through this slide to save some time. There's it just talks about some connection with, for the Yule distribution and how can be written in terms of d gamma function and so forth. So I think we can skip through this one and maybe go to the next slide that may be more interesting. So we want to go through some basic properties of the distribution, and then we'll look at some more interesting properties that go beyond the basics. So here are standard equations for the survival function, probability of greater than n, and those two probabilities, equal n, greater than n, they are simply connected in formula 25, and they both follow power law distributions. So as you can see, formulas 26 and 27 are talking about how these probabilities of equal n as well as greater than n actually behave like power law distributions. All right, so one important property of this distribution is the property of stability that is on the bottom of the screen. So actually, when we look at the excess of n beyond a given threshold m, then the conditional distribution of this excess, given that the random variable actually is greater than m, so that conditional distribution has the same kind of distribution. So there are some properties like this are common to some important probability distributions, and some distributions don't have these properties, but the generalized Shibuya distribution actually follows this property of stability with respect to to the excess. All right, so if you're below, beyond the threshold m, if you know that you are, then the probability of the difference n minus m is the same kind of distribution with different parameter v. Can we please move to the next screen? So then there are, moments of the distribution can be characterized as well. So because of the heavy tailness of the distribution and the behavior as a power law, as n goes to infinity, that not all the moments exist for this distribution. And if they do, they can be calculated by these equations that apparently use what is called Stirling numbers of the second kind. So the formulas for the moments are a little bit cumbersome, but they are given by relatively simple expressions. So we don't have infinite series or anything like this here. Just, they are relatively easy to calculate, especially by a computer. They can be effectively programmed to be calculated. Can we move to the next screen, please? So there are some standard results about these distributions, provided that they exist. So conditions must be put on the parameters in order for these moments to exist, like the mean or the variance. They may not exist if the parameters do not satisfy these conditions, but if they do, then they are given by relatively simple formulas. So one thing that should be pointed out here is that the variance is always greater than the mean, as can be seen by formula number 32. So in fact, these distributions are what is called over-dispersed. So the mean is always less than the variance. And there are some, you can study how this ratio actually behaves when either V or alpha is changing. Can we please go to the next screen? So then we have the probability generating function that can be figured out for this distribution as well. For the generalized Cebolla distribution, that probability generating function actually involves an infinite series, and it can be greatly simplified for some special cases, including the classical Cebolla distribution that is on the bottom of the screen. So it would be worth pointing out that for the classical Cebolla distribution with V equals 0, the formula for the probability generating function is actually quite simple. It's just 1 minus s to the power alpha. So that formula actually plays a very important role in the theory of this distribution and is responsible for many of its interesting properties. Can we please move on to the next screen? All right, very good. So here we start looking at some more interesting properties of the distribution, going beyond the basic ones. So first of all, one can understand this distribution in terms of a mixture of Poisson distributions. So when we look at formula number 39, then what it is there is a Poisson process N evaluated at a random x, where x is a positive random variable with the representation given by formula 38. So one can think of it as a Poisson random variable with the random parameter x. So this x is basically the mean of the Poisson, which is a random variable itself. So this particular representation implies that this Cebolla distribution is actually infinitely divisible, and interesting stochastic processes can actually be built upon this distribution. So the random variable x that appears in this representation is given in 38, is actually a ratio of two independent quantities, of which E is the standard exponential and T is another positive random variable, which is itself the ratio of two independent gamma random variables. So this is an example of what is called a, well, it's a mixture. It's basically a mixture of exponential distributions. Okay, let's go to the next screen. Perhaps we go to the next screen. We have some other representations of this Shibuya, generalized Shibuya distribution. Here's another one. You can think of this as conditionally geometric distribution. So here what we have is this random variable y. On top of the screen is the fraction between 0 and 1, and that's actually a beta distribution with two parameters, alpha and beta. The parameter beta is equal to 1 minus alpha plus v. So if we know the value of y, then the distribution of n becomes geometric with parameter p, where p is actually this you know, random beta random variable. So it's a hierarchical structure where conditionally on p, then this n is geometric, and p itself has a beta distribution of a certain kind with these two parameters. So it's a you know, mixed geometric distribution is another representation of the generalized Shibuya distribution. And then finally, we have the discretization scheme presented on the bottom of the screen. So there are many discrete distributions studied in the literature that actually are analogs of continuous distributions. They follow some sort of discretization scheme. One particular discretization scheme that is quite popular is to simply take an integer part of x. So if x is continuous, then integer part of x is discrete. And that scheme has been used for many probability distributions to obtain discrete version of continuous ones. In particular, if you start with this x that is given near the bottom of the screen, it's another mixture of exponentials, and we make this particular random variable discrete, then as a result, we actually get this generalized Shibuya distribution. So it can be obtained by discretization, a particular kind of continuous random variable x. Can we please move to the next screen? All right, very good. So we have the property of infinite divisibility. We've mentioned that one already. So x is actually equal in distribution to sum of n IID random variables for each and every integer n. And this generalized Shibuya distribution actually satisfies this property as well. It's an infinitely divisible random variables, and because of that, one can build interesting stochastic processes based upon this distribution. Those stochastic processes have discrete distributions at each and every t. So later, if this presentation, I hope that we can actually share some of these stochastic processes, not these particular ones, but different type that are quite interesting. They connect in a natural way in this particular distribution. Can we please go to the next screen? Okay, so here's another, and this property actually plays quite an important role in applications because it can be used to define some stochastic processes of discrete type. But let's start with this concept of a random variable n being self-decomposable and discrete. So what we're looking at in formula 44 is that on the right-hand side, we have, this operation. It's like discrete type of multiplication, C times N. It's not, it's not really times, because if we multiplied a variable N by a fraction C, then that variable will no longer be discrete. So it's defined in a little bit different way. The definition of this discrete multiplication is in the middle of the screen in formula 45. So actually what it is, the C times N, it's been introduced, I think in the 70s. So essentially what it does is we just add n number of independent Bernoulli random variables, and each one of those Bernoullis is with parameter C. All right, so basically because of that, the mean of this right-hand side is equal to C times N. So C times N is the mean of the random variable, but the random variable itself is not C times N. It's a discrete random variable, and it's precisely how this operation is defined. So a discrete self-decomposable distribution is one that satisfies this property 44, and it's actually true for each and every C that is between 0 and 1. So for each and every C, a random variable N can be decomposed in this particular way, where the two parts on the right-hand side are independent and the NC is also discrete. So this Shibuya distribution and generalized Shibuya distributions are both discrete self-decomposable. Can we please move to the next screen? All right, so here we are getting into some really, I think, very interesting results about this distribution. In fact, there is a characterization of the classical Shibuya distribution that is closely related to this particular representation. So we're looking at the classical Shibuya distribution with parameter alpha, which is less than 1. And then the NC would be the scaled Shibuya. So that's the Shibuya N multiplied by that C in the sense that we have just described. And it follows that, this result has been known, that basically when we multiply the C times N in this particular way, we get a discrete distribution. But that discrete distribution is actually very special. It's an actual multiplication of N and a Bernoulli random variable IC, which is Bernoulli with parameter C to the power alpha. So when we multiply N by this Bernoulli, we actually get either N or we get 0. So it's a mixed distribution with an point mass at 0 with probability 1 minus C to the power alpha, or it's an original Shibuya distribution with probability C alpha. So the question arises, if there is any other variable N that is discrete for which we have this kind of representation with not necessarily C do alpha, but some value of P that depends on C and is in 0, 1, and the answer is no. The Shibuya distribution is unique among all the discrete distributions. It actually follows this representation. So when we multiply N times C in the sense that was described, so the left-hand side in 46 is the discrete multiplication, that actually is the same thing as the regular multiplication, and you get N times an indicator random variable. So that's a very interesting property of the distribution. No other random variable n has this property here, and that property can be also illustrated by means of by the following result that I think we will have on the next screen. So if we can please move to the next screen that we can check it out. So yeah, so this is one more time that we emphasize this unique property of the Shibuya distribution. So in fact, because when we say that n times c on the left-hand side is the same as the Bernoulli variable IC times n, and again, the right-hand side simply says that it's either n with probability, or it's equal to 0, so it's a mixed distribution. But if we know that the random variable is greater than 0, so the conditional distribution on the left-hand side in 47, if we knew that that is greater than 0, then it must be Shibuya distribution. And that actually is true for each and every C in 0, 1. So no matter what that C is, the distribution of C times this discrete multiplication, given that it's greater than 0, has actually the same exact distribution as n. All right, so the faint random variable condition that it's positive is the same as n, regardless of this parameter c. And it's a unique characterization of this Shibuya distribution. Okay, can we please move on to the next slide? All right, so here is an interpretation of this result in an applied context. So if we have a bunch of IID random variable x, they are positive, you can think of these as some sort of random lifetimes. And the number of these lifetimes is the population size. So we start at time 0 with some number of individuals n. That's a random number of the individuals. And they've, each and every one of these individuals will have a lifetimes xi from 1 to n. And then we simply check how many individuals are still alive at time t. So we define the stochastic process nt given by formula 48. That's the number of individuals still alive at time t. It's called the pure death process. So it follows that if n has the Shibuya distribution, that's the n that we start the population with, the population size at time 0, then regardless of what distribution of x's are, that conditional distribution of n of t, given that n of t is greater than 0, is always the same as n. In other words, if we know that the population is still not extinct, if it's, some people are still alive in this population at time t, then the distribution is always Shibuya at each and every t. So it's some sort of stationary conditional distribution in this pure death process that the distribution is always the same at each and every t. And again, this is a characterization of this Shibuya distribution. So it's quite an interesting result, I think. All right, very good. So if we can please go to the next slide. All right, so let's talk a little bit about the connections of the Shibuya distribution and the extremes. So here is an interesting connection with, again, generalized type of distribution. So we know that if we have a CDF, this f of x is any CDF, and n is an integer, then when you take the power of the CDF, f to the power n, then that's always a CDF. That's another CDF. And in fact, this power of f is the CDF of the maximum of n random variables, of which each and every one has the same distribution f. All right, so if we take the maximum of x1 through xn, and these x's are independent, they follow the same exact distribution with the CDF f, then the maximum of this x's is another random variable x, and then the probability distribution of this maximum has the CDF equal to f to the power n. All right, very good. And then, but what happens if this n is not an integer, and if we raise the distribution f to the power alpha? That is not necessarily integer. So, you know, when we work the mathematics, it's clear that f to the power alpha is a legitimate CDF. It is around, I mean, it corresponds to some probability distribution, because it simply satisfies all the properties of CDF. And in fact, many probability distributions has been proposed as f to the power alpha, starting with the given f. So for example, if f is the CDF of exponential distribution, then f to the power alpha is a generalization of exponential called generalized exponential. And, you know, the same way we can have a generalized normal distribution, generalized Weibull distribution, generalized Pareto distribution, and so forth, simply by taking the power. And a similar construction can be applied to the survival function S, that is 1 minus f. So that survival function to the power n actually connects with the probability distribution of the minimum of n IID random variables. And again, s to the power alpha is also a valid survival function, but it doesn't have this interpretation. So actually what we'd like to do is to have some sort of interpretation for these fractional powers when alpha is not integer, and some sort of interpretation that is connected with the minimum or maximum as it is for integer n. And it turns out that Shibuya distribution can actually be used for this purpose, and we can have a connection with the minimum or maximum, even though the power alpha may not be an integer. Can we please move to the next slide? All right, so here's one result that is used to uncover this connection. This result is quite general, so in fact it has to do with either maximum or minimum with a random number of terms. So if we have a random variable n on the set of integers with the probability generating function gn, which is the expectation of s to the power n, and then we have a bunch of IID random variables xi, then when we take the maximum of those x's from 1 to n, so it's the maximum with the random number of terms n, where this n is independent of those xi, then the CDF of this maximum is actually equal to, you know, has this functional form gn evaluated at f of x. And the similar goes for minimum. When we take the minimum number of, you know, the minimum of those x's from 1 to n is actually gn evaluated at the survival function. So the survival function of the minimum is the gn evaluated at the common survival function of the x's, and the CDF of the max is the Gn evaluated at the CDF of the axis. All right. So if we want to follow the strategy and, and we want to have some connection with minimum or maximum, after all, we're looking at f to the power alpha and s to the power alpha. So if f to the power alpha, connected with the maximum of random number of x's, then we would have that Gn of f would be f to the alpha, and Gn of s would be s to the alpha. However, that's not possible because that would imply that the function g would have to have the form g of s equals s to the alpha, and unfortunately, that's not a valid probability generating function, so we cannot have that. However, we can have something quite similar, so let's go to the next slide to see what that is. Can we move to the next slide? Okay, so the resolution to this case here, in order to have what we want, we basically need to swap the roles of the minimum and the maximum, in which case we have the following result. So as we remember, the Shibuya distribution has a very particular probability generating function that is repeated here. It's 1 minus s to the alpha. And because of that, it leads to the following result. So if we have a CDF f, and then the corresponding survival function s, which is 1 minus f, that's the probability of greater than x, then when we do the expression, the survival function to the power alpha, or the CDF to the power alpha, where alpha is actually between 0 and 1, then these things actually have a concrete representation in terms of maxima and minima with the random number of terms. So in fact, the distribution of x is the random maximum of xi, and the distribution of y is the random minimum of the xi, where the number of terms of the maximum or minimum is the Shibuya distribution that is independent from those xi. All right. So, so the interesting thing here that when you look at the random maximum, that is distribution of x, then the survival function of this x is s to the alpha. Not the CDF, but the survival function is s to the power alpha, while the CDF of the y variable, which is the minimum, is the f to the power alpha. So that's, how we needed to swap the interpretation of the minimum and the maximum in order to achieve this goal. So basically, the bottom line here is that we actually have a concrete interpretation of a random variable whose survival function is s to the alpha, or a random variable whose CDF is f to the power alpha, where alpha is a fraction between 0 and 1, and both of them have to do with minimum or maximum, except that the number of terms taken is a random variable n having a Shibuya distribution. Okay, let me pause for a second. Are there any questions on this? All right, can we please move to the next screen?
Yeah, Professor, yeah.
And you know that result can be extended to going beyond a value from 0 to 1. In fact, alpha can be any any number from 0 to infinity. The screen got a little smaller. Can we increase the screen? Okay, so yeah, we're looking at an extension to any alpha. Thank you. Any alpha. So here what we need to do, we need to split this alpha, or actually let's call this number t. We can split it into its fractional and integer parts. So when the number t is strictly greater than k and less or equal than k plus 1, so it falls between two integers, and then we can take the integer part of this t will be called k, and the fractional part is the difference, it's t minus k. So this fractional part is going to be between 0 and 1, and the integer part is going to be an integer. If k is equal to 0, then this integer part, t in the curly bracket, would also equal 0. Okay, so then we have the following result. If we have a random variable x with this survival function s to the power t, where t is arbitrary number greater than 0, then when we split this t into the integer part and the fractional part, then we can actually write that random variable x as the minimum of two parts, where the left part is the minimum of xi from 1 to integer part of t, and then the part on the right hand side is actually a maximum of the xi, where the maximum is among the random number of terms, where the number of terms is the Shibuya random variable with parameter, which is precisely the fractional part of that t. Okay, and similar result applies to the CDF to the power t. When we take CDF to the power t, then actually we can break this down into the maximum of two random variables. That's the second equation in the formula 54. So here we're taking the maximum of xi's from 1 to the integer part of t, and then the second part is the minimum of a random number of xj's, where the number of terms in the minimum is again a Shibuya random variable. So are we done with the presentation? I think we're running out of time.
Yeah, it has to pin the screen. Pin.
So we have to stop the presentation, right?
Yeah, the presentation, no problem, Professor. It has some technical problem. It's coming now.
I'm sorry, I cannot hear. The voice is breaking. I cannot hear much.
Okay, Professor. Can you hear now, Professor? Can you hear? Now the presentation is coming.
So the question is, do we have to stop? We have to stop the presentation, right? Or should I move? Talk a little bit more?
Yeah, please, Professor. Continue,
so you want me to proceed? Okay.
Yeah, Professor. Yeah, please proceed.
Let's see. Okay. All right, so here's where we at. We are at this screen, right? Yeah, this is a good size. Thank you. So we are splitting the value t into integer and fractional part, And we basically have a representation for a random variable where we're taking either the survival function or the CDF to the power t, where t can be any arbitrary number greater than 0, right? This is our result. So can we please move to the next screen? So here are some examples of this, because this scheme is quite general. And actually, by taking the mean or maximum with the random number of terms, we can recover many other distributions that have been generalized in the literature. For example, there is a concept called Marshall-Alkene scheme, where a survival function S is used to generate an entire class of distributions with parameter alpha. That's formula 55. So as can be seen, this is precisely the distribution of either a minimum or maximum number of terms, depending on whether alpha is less than 1 or greater than 1, where the number of terms is a geometric random variable. So the Marshall-Alkene scheme can be thought of a distribution of a random number of IID random variables when you take either minimum or maximum of those, when the x's have the survival function S. So that's a common way to generalize a probability distribution. Can we please move to the next screen? Another such scheme that appeared in the literature is called Transmuted Distributions. So there is this concept of quadratic rank transmutation map given by formula 57. So here you start with the number u and you transmute it to another number, the right-hand side, that is also between 0 and 1, where alpha is a parameter between -1 and 1. And in fact, we can apply this transformation to any arbitrary CDF F, and we obtained another CDF out of this called F alpha. That's another generalization of a probability distribution. So we get a class of new distributions driven by parameter alpha between -1 and 1. And that scheme can also be shown to follow this particular scheme where, where in fact what we're doing, we're taking either minimum or maximum of random number of terms, where this time the number n is actually a Bernoulli distribution with parameter p shifted up by 1. So, you know, the value of this n is either 1 or 2. So we either have one random variable x, or we have two random variables, x1 and x2, and we can take either minimum or maximum of those. And that's precisely how we get a transmuted distribution. So it has similar interpretation. Can we please move to the next screen? Here is another example, number 3. There is a concept of Kumaraswamy distribution that has the CDF given by the formula on formula 60 here. And again, we can translate a distribution F into, insert this F for X into the formula for H, and we get a generalized version of a distribution F. So many such distributions have been proposed in the literature, and that scheme actually also follows this scheme with the either random maximum or random minimum of random variables with random number of terms. And actually these n's, the random number of terms, follow Shibuya distribution in this case. So again, I think we're gonna move through these examples maybe more quickly. Let's go to the next interesting development that is here. So let me say a few words on this, because that is actually quite what I consider quite interesting here. So there is some duality between the probability distributions that are operate on integers, and that duality is very special. So we know by now that actually any random variable n that is supported on integers can generate a new probability distribution from a base random variable x. When we actually convert this x into either maximum or minimum of values. So for example, let's say we start with an x has some sort of distribution. It can have any distribution. And then we use a random variable n to generate a new distribution called y. So y is the maximum of this x, x1 through xn, where these x's are IID, and n is an integer value random variable. So we start with an x called the base distribution, and we convert this x into the y, which is the maximum of x1 through xn. So the question is if we can reverse this process. So once we obtain the value of y, can we find another random variable n tilde in such a way that when we take those y values 1 through n and take the minimum of those, can then we recover the original x? So once again, we start with the x's, we convert them to the y by taking the maximum with n number of terms. And now we're asking, can we actually reverse this and using the y values by taking the minimum with another number of terms n tilde, can we recover the distribution of x? And if we can, then we call n and n tilde as dual pair of probability distributions. So in fact, it can be shown that we can obtain such dual pairs of distributions, as we will be seeing on the following examples. So let us please check, let us look at the next screen. So in order for these conditions to be true, you know, these variables n and n tilde need to satisfy some functional relation that is written in formula 63 and 64. So the g represents the probability generating function of the relevant random variables. So they need to satisfy this relation. In particular, g of n tilde needs to be related to g of n in a very special way given by formula 64. The formula 64 may produce something that is not a genuine probability generating function, but when it does, then that's exactly how we can obtain this dual distribution. So n and n tilde are called dual distribution with respect to the operation of random minimum and maximum, if that formula 64 actually produces a genuine probability generating function. Can we please move to the next screen? All right, so this is a symmetric notion. If n tilde is dual to n, then also n is dual to n tilde. And actually the four operation of taking the random minimum or maximum with either n or n tilde are always reversible and recover the original distribution. And there are actually many such dual pairs we can check what's the dual distribution to Shibuya distribution, geometric distribution, negative binomial distribution, Poisson distribution. All the standard distributions can be shown to have a dual distribution in this scheme, and that these dual distributions can be studied. So if n and n tilde are dual pair of distributions, then for any sequence, this xij are any IID random variables whatsoever, and the following relations are true. All right. So those x's that appear under the mean and maximum are independent from the number of terms. So basically, we can take first the maximum of x's, and then we can take minimum of these results, and we obtain the original x. And the minimum and the maximum can be done in two different orders, and the number of terms can be interchanged as well. So there are all four different combinations that this can be done. And in each and every case, we actually obtain the original distribution. So on the next couple of pages, we have examples of these dual pairs. So let's check them out, please. Maybe can we move to the next screen? So here's one dual pair. If n is deterministic random variable, means constant n with probability 1, then the probability generating function is just s to the power n, and the dual distribution to that one is the Shibuya distribution with parameter 1 over n. So, so dual to a constant is Shibuya with parameter 1 over n, but and if you have Shibuya with parameter 1 over n, then dual is a constant equal n. But if the parameter of Shibuya is not such that 1 over alpha is an integer, then the Shibuya has no dual. So not every Shibuya distribution has a dual. It does have a dual only if 1 over alpha is an integer. So that provides an example where there may not be a dual. Can we please move to the next one? So here is Bernoulli distribution and what kind of dual this one has. So when n is Bernoulli distribution with parameter p, we want to make this n start from 1. So we shift it up by 1. In other words, we take Bernoulli and we add 1. When we do that, we have a distribution with values 1 and 2, which is a random variable. It has a PGF given on top of the screen. And then that distribution actually has a dual. That dual is the formula in the middle of the screen. And the PDF of this distribution is also written there. It's probability n tilde equals n. And this dual is actually related to Shibuya random variable, and alpha is some sort of tilted distribution where we multiply the Shibuya probability by the power r to the power n and divide by expectation of this r to the power n alpha. And the value of r actually relates to the parameter p of the Bernoulli distribution, that you can see that on the bottom of the screen. So Bernoulli distribution shifted by 1 has a dual and is related to Shibuya distribution. Can we please move the screen up? Here are the duals connected with Poisson and logarithmic distribution. So if we take Poisson and truncate it below by 1, so it starts at 1 and not at 0. So it's the conditional distribution of n given that it's greater or equal than 1. Then the probability generating function is of the form 69. And this actually has a dual. That dual is given by formula 70. That's actually a logarithmic distribution. with parameter 1 minus q. So logarithmic and Poisson are two dual pairs in this particular scheme. And then I think we have one more example of this. Example number 4 is also there, where we have another pair of dual probability distribution, this one corresponding to a negative binomial random variable. Can we please move to the next screen? All right, so here's a negative binomial distribution with parameters R and P. That's the formula number 72. And we truncate the distribution below at 1, so it starts with the value of 1 rather than 0. The probability generating function of this truncated negative binomial there is formula 73, and we can actually work out a dual distribution to that one, and it looks very similar to negative binomial. In fact, it is a negative binomial when you look at formula 74, and the parameters have changed to 1 divided by r and p to the power r. So a dual to negative binomial is another negative binomial. They have a dual set of parameters. And in particular, when we start with the geometric distribution where r is equal to 1, then we find that the dual is the same geometric. So the geometric distribution is a dual to itself in that particular probabilistic scheme. I think that concludes the examples for the dual pairs. And so I'm afraid we are out of time probably, right?
Doesn't matter, Professor. Since okay, Professor, it is out of time.
So I should stop now, right? I think.
You can take some more time to conclude, Professor. That's good.
Or do you want me to continue a little bit more?
Yeah, Professor.
Because I'd be happy to continue. I just don't want to keep you for a long time. But I can go on for some more time if you wish.
Yeah, that's left to you, Professor. If you are.
All right, very good. So let's do a little bit more of the presentation. Okay. Can we scroll down, please?
Yeah, Professor. Yeah, Professor.
Can we scroll down to the next screen? All right, so basically the theory that we lay down for the minimum and maximum, this can actually be repeated in terms of the bivariate distribution. So we can start with the sequence X, IID random variables, and we can actually look at the minimum and the maximum together as a pair of random variables. So in fact, we can work with deterministic n and look at the minimum number of, the minimum value of x's together with the maximum value of x's. And we can study the joint distribution of the minimum and the maximum. And this joint distribution has a well-known structure given by formula 75. And what we want is to extend the bivariate distribution to the case where n is not necessarily an integer. So the question we're posing is, can this be done? Can we have some sort of bivariate distribution that is valid for arbitrary n, not necessarily an integer, but when n is an integer, it will reduce to this distribution. And it turns out that such an extension is actually possible and will be presented on the next couple of slides. Can we move on the next one, please? Okay, so here is the actual result. So if t is an arbitrary number between 0 and infinity, not necessarily an integer, we can split that t into its integer and fractional parts the same way we've done this before in connection with univariate distribution. And we can look at a pair of random variables that we call x and y. So x is actually a minimum of two components. So that's the left point in the bracket there. So we take the minimum of xj from 1 to an integer part of t. There is a concrete number of terms, which is not a random number. It's a deterministic minimum. And then we take the minimum of this one with a random maximum of xj's, where the number of terms in the maximum is actually a random variable which has a Shibuya distribution with the parameter which is a fractional value of t. And then the component y actually has to do with the maximum of two values, of which the first one is the maximum of the xj's, and we take that maximum of the minimum with the random number of terms. Okay, so this nt, that is the random number of terms, is actually the same on, both in x and y. And it can be shown that the joint CDF of this construction is given by formula 77. So there's some sort of joint distribution that can be constructed from the xj's and the Shibuya distribution. And what is interesting here, that the marginal distributions of x and y actually follow the structure where the survival function of x is equal to the survival function to the power t, and the marginal CDF of y is the CDF to the power t, where this s and f relate to the sequence xj. So xj, you can think of a base random variable that has a CDF capital F and the survival function s, and we can actually construct a joint distribution where the first component has the survival function to the power t, and the second component has the CDF to the power t. Okay, and then also when t happens to be an integer, then we recover the distribution of the minimum and maximum. The well-known result for the lowest order statistic, and the maximum in the sample is recovered when n is actually equal to t. But that construction is valid for arbitrary t. It doesn't have to be an integer. In fact, what is interesting here, we probably won't have time to go into details, but one can produce a stochastic process that has the same structure. That is, at each and every t, the survival function of the first component is s to the power t, and the CDF of the second component is the CDF to the power t. Can we please go to the next one? So here's some further details about this joint distribution. Here it's presented in a little bit different way. And in fact, this joint distribution is now very fashionable to define the distribution that are multivariate through the so-called copula representations. So in fact, there is a particular copula C that connects with this sort of bivariate distribution. So what we mean by this is that the joint CDF is equal to the function C evaluated at the two marginal CDFs. So it's C of f of x and fy of y for each and every input x and y. And the particular copula C that connects with this particular construction then is given on the bottom of the screen. So this is a generalization of the minimum maximum copula that is connected with the distribution of the minimum and the maximum of the xj, where the minimum and maximum are calculated for j between 1 and n, when n is an integer. So this is a more general model that generalizes this min-max copula, and it works with arbitrary alpha that is greater than 0. Can we move to the next one, please? Okay, so, and then there are more generalized results to this. There are some generalizations that go beyond Shibuya distribution. In fact, one can construct many bivariate distributions by following this scheme. And in each and every case, there is a particular copula representation and copula function that actually can be defined based on an integer valued random variable n. So for Shibuya distribution, we have one particular copula function. For other random variable n, there will be a different copula function. And we can have many interesting bivariate distributions that connect with this random extrema. Can we go to the next slide, please? Okay, I think we will skip this. We can also have like the general, more generalization in this direction. So I'm not sure if maybe we don't have time to get into this random process. So there is also a random process that can be constructed. Maybe I should say just a couple of words on this. And maybe if we can scroll down a little bit, there is a picture there that we can go over. The picture would be more constructive than reading all these details. There's a lot of write-up here. But I think we'd like to maybe check the picture there, and then I can explain this a little bit, this picture, if we can get to that screen, because that picture is actually interesting, and it will explain much better than this write-up of what the process looks like, since we essentially ran out of time here. So yeah, can we go a little bit more downward direction? There we go. Okay, so so on this picture, let's see if we can explain this a little bit. So think of a sequence of random variables un. So there's u1, u2, u3, and so forth, and independent standard uniform random variables. Those uniform random variables are multiplied by integer. So there is a variable u1, that one is on the very bottom. Then there is 2 times u2, and then there we have 3 times u3, 4 times u4, and so forth. So those uniforms multiply un times n are represented by the horizontal arrows that start with 1 and point to the left. So basically the arrow on the very bottom is just u1, so that one is going to be less than 1. And then, the further up arrows, are also there, and they are all independent random variables. The size of all of these variables are independent. And basically, when you look at the record values, so, the one on the bottom, and then you're looking at the next one that will be less than the one on the bottom, and that happens to be 5 times u5, which is presented in blue dashed line. That is the very first one that was less than U1. And then the following one would be 9U9 and so forth. But anyway, what I'd like to say here is that one can actually define a stochastic process that is given by this red line here that starts at the level 1 and then is constant until it jumps up to a random location. This random location is 5. Then it stays level until it has another upward jump, J2, and then it stays level and jumps again and so forth. And all I want to say at this point is that it's some sort of random process where at each value t, the position of the red line is actually a Shibuya distribution. So there is a Shibuya distribution that behaves this way. It's a bunch of infinitely many random variables put together into this interesting stochastic process. And this stochastic process can be studied further. It has many interesting properties. And let me just finish by saying that, to get more information about this, it can be found in the relevant paper. So I think with that, I would finish this presentation. I'm sorry I went a little bit over time and there was some technical issues that I apologize. I have never used this system before, and I struggled a little bit. I usually have meetings in Zoom where I know how to share my documents, and with this Google meeting, it's a little bit different. But I'm glad that we managed to go through the presentation. Thank you.
Thank you, Professor. Thank you so much.
Are there any questions?
Hello, Professor Tom.
Yes, hello, how are you? Nice to see you. Good to see you.
Yeah. It's a long time we have met. Right.
Right. I hope everything is all right there at your end.
Yeah, everything is right.
It's very challenging these days.
Hey. And in fact, you have made an interesting work on the classical severe random variable and its extensions. Right?
That's right. That's correct.
Yeah. And I have one comment. That is, the fundamental assumption that we are looking in the severe case is the probability is inversely proportional to the trial number.
That's correct. That's correct.
Yeah. Is there any other variant in these assumptions? That is, suppose you are assuming that it is raised to some power. It is just like probability that n is equal to j is j raised to alpha, or some other versions. Have you seen any other work relating to that? That's that type.
So they not particularly, but many such schemes can be defined and studied.
Yeah, I was thinking over that, but I haven't.
I haven't seen much work in this direction, no, but there's a lot of room to study these extensions. For example, you can take powers and other functions and study the probability distributions. That's true. That would be very interesting.
Oh. And you have done some fundamental works in this direction. That is, you may be able to define the random variable corresponding to the fx raised to alpha, where alpha is a fraction.
Yes, that can be done. So one can define such a, Bernoulli trials through these powers of alpha and study the probability distribution. That's correct. That would be very interesting, I think. That will be more generalized distribution. If power is 1, then you recover this distribution.
This distribution.
Right.
Okay, sir. Thank you. Thank you.
Thank you.
Okay, thank you. Thank you, Jagama.
Thank
Any
you.
other comments or questions? One more, I hope, if anyone is interested. If you want, you see my etc. details are available, and in our conference site.
You can also share, if you go to the very end of the presentation, there are some references there that maybe should be shared in case anybody is interested. There are references in there listed at the end.
Reference.
At the end of the presentation, there's some references listed, and you know, some of these references may be of interest. You can find further details in there if you're interested about this topic. So there are some papers we have done, and there's some papers on Shibuya distribution in general.
Okay, Professor. Yeah. Yeah. Now let us, if there is no questions and comments, let us conclude this session. In fact, we have a very nice session. He has taken a lot of pain to prepare all those materials and present in a beautiful way. A researcher there's a lot of opportunities to do something in that direction. Our researchers are lucky to have Professor.
I'm very glad that I can contribute to the workshop. I'm very glad to be here and see you there, everybody there.
We hope your support will be there for in future also.
Sure.
Next year.
I'm always happy to contribute. Thank you.
After Corona, you are most welcome to the department. And after this pandemic situation.
Yeah, thank you very much for this opportunity, and I will be in touch with you. I'd like to attend some talks tomorrow. There will be some more talks, and I'm afraid I may have an issue with joining the meeting. So I'll be in touch by email.
Surely, Professor, let us. Yeah, we can.
I'd like to join the sessions tomorrow as well to listen to some presentations.
Yes, that's good, Professor. That's good. Yeah, that's good. Yeah. Tomorrow we have today evening also a session.
That one I probably cannot attend because it's a very different time for me. Because of the time difference, it's difficult for me to attend. But there will be some sessions the next day that I think I would like to attend. So I'll be in touch by email.
Yeah, Professor. Yeah. Tomorrow morning session, Professor Kundu will.
That's what I'm talking about, the morning session.
Yeah. Thereafter, Professor Jagimar also join with us, another continuing session. Anyway, we are very lucky, and we have. I utilize this occasion to extend our gratitude, Professor, on behalf of the Department of Statistics, University of Kerala. We extend our heartfelt gratitude to Professor Thomas J. Kusumowiski.
Thank you very much
for nice.
Thank you very much.
Thank you so much. Thank you. Let us give a big clap to
Thank you.
Professor. Yeah.
It was very good to see you. Thank you.
Thank you so much.
I'm glad to participate,
Yeah.
as always. Thank you.
Yeah, Professor. After this, we can interact, Professor, for doing that presentation problem. If
That's
you are
right. Do you
free
want to
now,
interact now or later? When should we interact?
now it's better after all the participants are leave from this meet. I shall explain how to present
Okay, so should I
these
stay?
materials so that
I should stay now, right?
you have to definitely.
Okay,
Yeah.
I will.
Yeah, Professor. Yeah.
Thank you.
Yeah. Thank you so much. Thank you all. Thank you all the participants for your support. And my students and other professors. I think Professor Hirakawa also joined in the meantime with us.
Okay, very
Yeah.
good. Thank you.
Yeah.